The rate law. Now, the balanced chemical equation gives us information about the overall reaction, but it doesn't really tell us anything about how quickly or how slowly a reaction occurs, i.e. the rate of the reaction. If we look at this example here, we know that 1 mole of CH3Cl is going to react with 3 moles of Cl2 and to produce some products. Now, if I change my concentration of CH3Cl, that doesn't really tell us whether my reaction is going to occur more quickly or more slowly. It just tells us that potentially if I increase the amount of CH3Cl and I increase the amount of Cl2, I'm going to get more products. But it has nothing to do with how quickly that will occur or how slowly that will occur. This can only be determined using experimental evidence. So let's take a look at a general equation here. I'm just going to grab a pen. And so we've got two reactants, X and Y, and they are raised to the coefficient of A and the coefficient of B respectively. If we were to write the rate law for this particular reaction, it would be proportional to the multiplication of my initial concentrations, i.e. multiplying my X and my Y together, and raising those values to some concentration M and some concentration N. Now you'll note that M and N are very different than A and B. I did not use the same letters. And that's because the M value and the N value can be different than the coefficients. And most often they are different. There's only one situation where the coefficients of a balanced equation match up with these exponents. And we'll talk more about that later. So if we were to write the rate law, it would look something like this. The rate of the reaction is going to be proportional to the initial concentration of my X raised to some exponent M and the concentration of Y raised to some exponent N. And to turn it into an equation, well, we just have to add some kind of a constant here. So this is a general form of my rate law. It has the concentration of my reactants, and those reactants are raised to the exponents M or N. So let's write this down. So the coefficients of your balanced chemical equation may or may not be the same as the exponents of the rate law. The only exception when they are the same is when we deal with a single step mechanism, and we will talk more about that later. Secondly, since rate is dependent on the concentration of my reactants, you'll always find the reactants in your rate law. Now, there will be an occasion where the reactant will have no effect on rate, but I'll let you figure out when that situation is and what exponent we're dealing with when that occurs. So let's look at some real experimental data here. So I've done this experiment, and we've done it 4 different times with varying concentrations of CH3Cl and Cl2, and we've measured the rate that the hydrogen chloride gas has produced. As in any good experiment, if we want to figure out how, let's say, my Cl2 affects my rate, we need to do a couple of things. First of all, we need to only vary one variable at a time. In other words, I can't change my CH3Cl and change my Cl2 and expect to know how only Cl2 affects my rate of reaction. What I want to do is I want to keep my concentration of my CH3Cl constant and just change the concentration of my Cl2. So in this case here, I think I'm going to be using experiment 2 and experiment 3. Now let's look how this looks when we put it into our rate law. So there's my data once again. And once again, changing only one variable at a time. So experiment 2 and experiment 3 is what I'm most interested in. And what we're going to look for is the ratio between the concentration of my rate of reaction. So we're going to look at the ratio of my rate of reaction compared to the ratio of my Cl2 concentration raised to some exponent. So data once again, and I like to keep things in whole numbers. So I'm going to choose to put experiment number 3 in the numerator, just because the values are larger and that'll give me nice whole numbers. You could do it with fractions, but whole numbers are easier to work with. So those are the 2 experiments that I'm going to use. I'm going to raise it to some exponent m. That's what I'm looking for, because I don't have any values for that. I'm going to use the data to figure out my m value. I'll sub in, And so I end up with my rate changes by a factor of 4, and to get that statement to be true, my concentration of Cl has changed by a factor of 2. I need to find out what m is. Well, to make that statement true, the value of m has to be equal to 2. Therefore, the rate can be said is proportional to the concentration of my Cl2 raised to the exponent 2. What does that mean? Well, when the concentration of my Cl2 changes, the rate changes by the exponent 2. So if I triple my concentration of Cl2, my rate is going to change by a factor of 3 raised to the exponent 2, or a factor of 9. So here we see that Cl2 really does have an effect on my rate of reaction. If I change the concentration of my Cl2, my rate's going to change significantly by a factor of the exponent 2. Now we're going to look at what happens when I change the concentration of my CH3Cl. Well, in this case, I want to keep my Cl2 concentration constant because I'm not looking at that anymore. And what I want to look at is the change in my CH3Cl. So in this case, experiment 1 and experiment 2 offer some good data for us to look at. Once again, keeping whole numbers, so I'm going to put experiment 2 in the numerator and experiment 1 values in the denominator. This time I'm looking for a different exponent. I'm looking for the exponent n. Sub in my values, and now I need to make that statement true. What does n have to be? Well, to make the statement true, n has to be a value of 1. So my rate varies with the concentration of my CH3Cl raised to the exponent 1. What does that mean? Well, when the CH3Cl concentration changes, the rate changes by the exponent 1. In other words, if I triple my concentration of CH3Cl, well, 3 to the power of 1 means my rate changes by 3 times. So here we can see that changing the concentration of my CH3Cl does not have as much of an effect as changing the concentration of my Cl2. If you remember, right, Cl2 changes concentration, the rate changes by the exponent 2. Change my CH3Cl concentration, my rate's going to change by the exponent 1. Now, all we need to do to make this into an equation is figure out our value for k. And to figure out the value for k, we can use any set of data that we want. So I'm just going to choose experiment 1. So I'm going to sub in my rate that I got from my data on experiment 1. I'm going to sub in my concentration of my CH3Cl. I'm going to sub in my concentration of my Cl2 along with the units. The units are important. And I'm just going to solve it through. Now note, my Cl2 is raised to the exponent 2. That's why I end up with moles squared and liters squared. Continue to simplify. And now I got to do a little bit of canceling. So liters here is in the denominator. Liters here is in the numerator. So this becomes liters quantity squared. Mole is here. Going to get rid of that. And this becomes mole quantity squared. So my final units, and I made a mistake here, this should have seconds in here as well. I'll fix that later. And so this is what I end up as my final units. Now, don't memorize your units for k because they'll change. Your units of k are dependent on what the exponents are up here. So you'll have to figure it out each and every time. Or if you see a pattern, it will make your life easier. So what do we say about these exponents? We call them orders. So the overall order for this reaction is simply the sum of your exponents. So 1 plus 2, so the order is 3 for the overall equation. And we can also say that with respect to CH3Cl, it has an order of 1. With respect to Cl2, it has an order of 2. And once again, if you know the overall order, look for a pattern for figuring out your units of k. See if you can see it. And that's your rate law.